All right, here we go. Take two, talking about conservation momentum. We said in the last video a couple minutes ago that the initial momentum, try that again. Where are we at? There we go. The initial momentum you start out with in a system is the same amount of momentum you have to start out with it. And we're going to use a similar example to what we had last time. Our system is only what's in this box, and our objects are one traveling to the right, one traveling to the left. Alright, before we start throwing numbers in here, let's get the equation stuff out of the way. The momentum of the first ball initially is P1I. The 1 meaning the first ball here, the I meaning its initial momentum. This ball here being ball 2 is going to be P2I. That is its initial momentum. Ball 2, initial momentum. Now, a short time later, they are going to collide. Now, once they collide, their velocities are going to change, which means their momentum is going to change. We'll just say they bounce back in opposite directions. This ball is going to be going to the left now, and this one here is going to be going to the right. Their momentum has changed. For no other reason than their velocity and direction has changed. This ball here is still 1, this one's 2. This ball here, its momentum at that point is going to be P1 since it's ball 1, but F. So now we're going to be looking at its final momentum. And this is going to be P2F. You could do this for 3, 4, 5 balls. If for some reason we had another ball over here or one up here, we would call that ball 3. We would then just say P3I. But we're not going to start messing with 3 objects. Let's just stick with 2. The initial momentum of this system here, remember this is our initial, is the momentum of this ball and the momentum of this ball summed together. In other words, the initial momentum is equal to the momentum 1 initial plus the momentum 2 initial. Oops, sloppy. Okay. Likewise, down here, the momentum final is equal to the momentum of ball 1 and its final momentum plus the momentum of ball 2 and its final momentum. Now, a little bit of substitution. Take these two, bring it up here. We can see that the initial momentum from ball 1, let me stay with the proper notation, 1I plus P2I equals, I just wrote down the initial momentums, which are right here, and what are they equal to? They're equal to the final momentums, P1F plus P2F. So if I can find the initial momentum each of the balls start with, then that should be equal to the sum of the momentums the balls end with. Alright, this is useful if you understand the momentums of each one of the ball. However, most of the times it's not easy to measure the momentum of a ball. We can measure the mass and the velocity. The momentum of any object is its mass times its velocity, or the initial momentum of ball 1 is equal to the initial velocity of ball 1 times its momentum. Likewise, we do the same thing. Whoop, a little too far. The initial of ball 2, or let me say 2I, or in other words, any momentum we're looking for, we have to use the corresponding velocity. Let's see if I don't go too far this time. There we go. So the initial momentum of ball 1 is mv1I plus the momentum of ball 2 initially, m2. Wait a minute, that's not 2. Sorry. v2I equals the momentum of 1 final is the mass times the velocity 1 final plus the momentum of ball 2 final, mv2f. This is the expanded version of the 2-object conservation of momentum equation. And what this says is whatever initial momentum you start out with between the 2 objects has to be there at the end. Now, what can change in this equation? A couple things can. Most oftenly, when the momentum of an object changes, it's not the mass that changes. When two cars collide, there's still two cars afterwards, same amount of everything inside them. Even when a grenade explodes, if you add up all the mass that the grenade starts with and compare it to all the gases, the shrapnel, the expanding liquids, or anything else that's made up of matter, it's all still there afterwards. It's just looking a little bit different. So the momentum before will be equal to the momentum after. Let's use this situation up here and see what it's going to be like afterwards. Let's say this object here, this ball is going to the right at 5. This one here is going 4. Right? The ball initially for object 1 is going 5, and for 2 it's going 4. Finally, the ball afterwards for 1, let's say it's going to the left at, let's say 3. For a second, I'm just kind of pulling numbers out of the air. We want to find out how fast this ball here is going, ball 2. We want to find out its final velocity of ball 2. Right. Sometimes these subscripts get rearranged, but V2F is the same thing as VF2. Right. And the last thing we have to know the mass of these balls. Let's assume that the mass of ball 1 equals 2 kilograms, and the mass ball 2 equals 3 kilograms. Right. Lots of variables to keep track of here, but it's not really that bad. Let me see if I can. Yeah, I'm not going to bother with that. I'm just going to go to a wider view. Alright, so we're going to take all these variables up here, throw them down this equation, and see what we get. The mass of... Oh, I apologize. I did forget a couple subscripts in this equation. If you're looking for the initial mass of object, or the initial momentum of object 1, you do have to use the mass of object 1. Right. If you're looking for the initial momentum of object 2, you also have to use the mass of 2. So there's a couple subscripts I've forgotten here. 1 and 2. Right. Need to, you guys can come back in the video in a second and make that a notation in your notes. Okay? And these are all products. They're all being multiplied. Dots. Okay. Now, here we go. The mass of object 1 is 2 kilograms. The initial velocity of object 1 is 5 meters per second. Plus the mass of object 2, 3 kilograms, times the velocity initial of object 2, 4 meters per second. If I wrote that down, I would be wrong as all wrong. Because what is the big difference between object 1 and object 2 in their velocities? They are traveling in opposite directions. We're going to have to call one direction positive, and one direction negative. To the right will be positive, to the left is negative. Object 1 is traveling to the right, positive. Object 2 is traveling to the left, negative. Forget this step and take care of the negatives. It causes huge problems with this equation. Okay, now we're on the right side. The mass 1 is 2 kilograms times the final velocity of object 1. The final velocity of object 1 down here is 3 meters per second. Right, plus the mass of object 2, which was 3 kilograms, times the final velocity of object 2. Final velocity of object 2 is something we don't know. V2F. This is what we're going to solve for. And as you see, something different than what I normally do. I usually solve the equation for the variable, then plug numbers in. At first, it's probably best just to plug the numbers in and then solve it that way. After you get a little bit of practice doing so, then start solving that equation. Or if you're confident in your algebra skills, you can do it either way. Okay. So we have 2 times 5 is 10 kilogram meters per second, plus 3 times negative 4, negative 12 kilogram meters per second, equals 2 times 3, 6 kilogram meters per second, plus 3 times V2F kilograms. Okay. 10 minus 12, we have a negative 2 kilogram meters per second equals 6 kilogram meters per second plus 3 V2F kilograms. Okay. So let's, oh, I'm sorry. Let's subtract 6 kilograms from both sides. There's 6 kilogram meters per second from both sides. And when we do so, on this side it goes away. On this side we have negative 2 minus 6, negative 8 kilogram meters per second. And on the right side we have the 3 V2F kg. Just divide both sides by 3 kilograms. And you'll see the final velocity is 8 divided by 3 was at 2.67 negative meters per second. And these kilograms cancel out. And that equals the final velocity of the second object is 2.67 meters per second to the left. Or I'm sorry, is that true? It's going to the right. Where do we make a mistake? Alright, we have to the left is negative. So we had the first initial traveling positive, the second one traveling negative. Initial final velocity of object 1. There we are, right there. This object should be negative. 3 meters per second here should be to the left. Should we? Yeah, because here it says it's going to the left, so this should be negative. That means if we go back through, this should be a negative here. When we take 6 to both sides, we should be adding it to get rid of this negative 6. So that means this here will be a positive 4, and then 4/3 positive, that's not true anymore, is 1 and 3/4. Alright, firsthand, physics teacher, you saw even make simple mistakes with these directions. So whenever you're solving problems, make sure every time you write down what the velocity is in these equations, make sure you're double checking to see if they're positive or negative. Because I guarantee it's going to happen at some point with you solving these problems. You're going to forget or forget to take care of this positive and negative. We all do it. So that is conservation of momentum in a nutshell. These are the basics of it. Go ahead and start working on some problems. The best way to get good at it is just to practice. You will not have mastered just from watching these videos. Anyway, that is all. Have a good day.